I'll just go
ahead. Okay. Can you see the screen?
Yes, it's running, and we can hear you. So.
Okay, perfect. Thank you for the introduction, and hello everyone. So as you say, I will present about the production of chitin nanofibers from insects, and I will compare them to conventional sources. So first thing, why do we want to use insects? One reason is that because of the world population is increasing, there is also an increasing demand for food and for protein. And the conventional sources for protein are, as you know, like meat and fish and also some plant-based food. And they are not very sustainable, especially for the meat part. And for the fish, we also have some extensive fishing, which is not also not sustainable. So we need to find better solutions and to replace these sources of protein. And as you can see here, maybe I will, yeah. So these are some potential future foods that can replace the conventional sources for proteins. And among them, you can see that 3 of them are actually insects. So why insects are more sustainable? Here we analyze a life cycle assessment of mealworm farming. And you can see that the land use is actually quite low compared to the meat sources. And also the emissions are low, so it has low global warming potential. One thing is that the energy used to produce the mealworms is quite high, but this is due to the heating of the rearing facilities, and it can be overcome if you go to a warmer country maybe, and then you need to heat less. So there is low surface, and this is mainly due to the possibility to do vertical farming. So they actually made it like in big, I would say it's industry, and you kind of pile the mealworms so that you have this vertical farm. And low emissions, and we also have a high protein ratio, so the insects contain a high amount of proteins. So that's why they also want to use them as potential source of protein. And another thing is that it can be really easily fit in the circular economy, because the insects can be fed with food waste or agricultural waste. So here is the example of fly, and it's fed by food waste, as I said, and then you have a very short life cycle of 45 days. And from this, you can produce some protein and also some chitin. So several advantages, and also they consume very low amount of water, and you don't need water to produce their feed, because it's only waste. And also it has been shown that they contain all the essential nutrients for human consumption. So this is actually a growing industry. It's quite new, like 10 years. It started 10 years ago, but it's growing quite fast, and there are already some pilot scale and even industrial scale production of insects. And what interested us is the chitin. So the chitin is present in the exoskeleton of the insects. And it can be extracted as a side of the protein extraction. That is now the main purpose of this industry. So our study here was to compare chitins that were extracted from 2 different insects. And we compared with conventional source, which is a commercial chitin from shrimp. And the insects chitin were from one fly and one mealworm. So the mealworm was actually only the exuviae of the mealworm. So it's the skin that they remove when they grow. And so it's really a waste from the industry because they don't use it to extract proteins. And after some purification steps, we obtain different chitin fibers. And after that, we produced some chitin nanofibers. So here is the high pressure process that produced the nanofibers. It's quite similar to the cellulose nanofibers production process. And at the end, we want to form some films from that, and we also characterize them. So the goal is to see first if we can produce some chitin nanofibers from the insects and how they are compared to the conventional shrimp chitin. So first, the purification step. So the main components in the insects are lipids, proteins, and minerals. And we have a 4 steps process for purification. The first one is a Soxhlet extraction to remove the lipids. Then we have demineralization to remove some minerals, and deproteinization with basic conditions to remove the proteins. And then we have a final step, which is bleaching to remove some residual pigments. So we obtain the 3 different chitin, and we characterize this. So we did some carbon NMR on the different chitins. And as you can see with the first spectrum, this is the chitin from shrimp, and it really fits the NMR of chitin. We don't have any additional peaks. For the fly, we have a small region here where we have some very small peaks, and this could be due to the small amount of proteins, but we were not able to quantify because it's really small. And for the worm sample here, we can find 2 additional peaks, and we will see after what it's exactly. So we also did some analysis, ash content analysis to see if there are some minerals left, and it's actually quite low. So we have some purified chitin from shrimp and fly, and for the worm we have a mix. And so we analyze further this NMR, and if we compare it with the cellulose, the NMR of cellulose, we can see that these additional peaks that were appearing before are actually coming from some cellulose. And this is actually due to the presence of some feed of the mealworm that were present in the waste that was given to us. And so we quantified the cellulose and chitin ratio, and it was actually quite high. So it was 50% of cellulose in the sample. Then we continue with the fibrillation of these different chitin fibers. So we use high pressure fluidization with micrometer chambers to produce these nanofibers. And we do it at pH 3 because then we can have some charge that help the fibrillation. So first we look at the morphology of the different nanofibers with AFM images. Here you can see that we obtain really nice nanofibers for the 3 different chitins. and the profile of the size are quite comparable. We also look at the bulk suspension, so to see if we have some aggregate in the suspension. And here you can see that there is actually a difference between the shrimp and fly. So the fly has higher transmittance of the suspension, which means that the fibrils are smaller and we have higher fibrillation. And this is due to the porosity of the fibers, because the insect fibers have higher porosity, so they're more accessible for the fibrillation step. Then we look at the surface charge of the different nanofibers. So you can see that at acidic zeta potential, chitin has a positive charge, which is the normal, because you have an amine group on the chitin. And for the worm, it's negative because of the presence of cellulose. And we look also at the zeta potential at neutral pH, and for the worm it was actually more stable, lower zeta potential. So for the next steps, we also process the worm at neutral pH. We also measure the charge content with conductimetric titration for the different fibers, and we obtain quite a similar charge, except for the worm that has higher charge, and here it's also due to the combination of cellulose and chitin. Then we were able to measure calculate the degree of acetylation, because in the chitin we have always some acetylated part. That's actually the main part of the chitin, and then some groups are deacetylated to form the amine group. And that's when we have mainly acetylated groups, then it's chitin, and the difference with chitosan is that chitosan has mainly deacetylated group on the surface, and it makes it also soluble in acidic pH. But here we want to keep the acetyl group, and so we have the nanofibers that are not soluble. So here the degree of acetylation are also quite similar between the shrimp and the fly. And we also look at the structure of the fibers with XRD, and we have the characteristic peak of the alpha allomorph of chitin at 19 and 9 degrees. And so this has been reported before, that the insect chitin is also alpha allomorph. For the worm, again, we have the presence of cellulose that makes some additional peak here with the dashed lines. Then we processed some films from this different nanofiber suspension. So we used filtration, and then we used two different conditions for drying the films. One was hot press for 30 minutes at 90 degrees under pressure, and the other one was cold press. So it's no temperature and overnight drying under weight. And we for the worm, as I said before, the suspension was more stable at pH 7, so we also processed it at pH 7. First, we'll just look at the aspect of the film. So you can see that the first one are cold press, and then the shrimp and the fly that were hot pressed. You can see here high difference in transparency. And for the worm films, we cannot see a huge difference between both. So the pH didn't really have at least visible influence. No visible aggregates were present at pH 3, so it was quite good. To measure the transmittance, we used the UV light spectroscopy. And as you can see, between the cold press and hot press again, we can actually measure the transparency, the difference in transparency. It's quite high. And we also have a difference between the shrimp and the fly sample. And as we've seen before, this is due to the higher fibrillation degree of the fly. Then we look at the mechanical properties of the different films. So you can see that the hot press films again have very different behavior than the cold press. They have higher Young modulus, but way lower elongation. And this is due to the fast drying of the fibers that will change the interaction between the fibers and makes the film stronger but less elastic. And you can see that the difference between the shrimp and the fly are quite low, and that the process has way more influence than the precursor of the fibers. And we can also see that the samples from the worm have actually really good elongation and toughness. And we also look at the cross-section of the films, and you can see that they have this paper-like structure, all of them with the fiber in the plane and forming layers. And no visible aggregation again was visible in the worm sample, even at pH 3. And to understand better the properties of the worm sample, we did engineer some films with 50% of cellulose nanofibers and 50% of chitin nanofibers from the shrimp. And here you can see that the film with 50% was actually had intermediate properties between the cellulose and the chitin nanofibers. So one explanation why we have higher properties for the worm, it could be because we have the presence of cellulose nanofibers in the samples that increase the elongation, but it's not enough because we still have a way higher elongation. And this could be due to residual proteins that act as a plasticizer in the film. Or it can be also due to the fibrillation that was done together for this. So the cellulose and chitin were fibrillated together and then closely mixed together, so we can also improve the interaction between both fibers and improve the elongation of the film. So to conclude, we have extracted some chitin nanofibers from insects, and they were well purified. And we also used the waste from mealworm that contains 50% of chitin and 50% of cellulose. We did fibrillate these chitin fibers to obtain some nanofibers, and the morphology and also the degree of acetylation and crystallite form was quite similar for the different samples. But we've seen also that the chitin nanofibers from fly were more fibrillated than the one from shrimp. And for the film formation, we've seen that the drying process has really more influence than the precursor of the chitin. And we also seen that we have improved properties in elongation and toughness for the film from the mealworm nanofibers. Yeah. So we can conclude that the chitin from the insect are quite comparable to the one from shrimp, and they even are more easily fibrillated. And we also did valorize the waste from mealworm, and it can be used actually without any separation. Some perspective. So we've seen that chitin is a byproduct from the insect industry, and these chitin nanofibers can have several applications, ranging from Pickering emulsions, biomedical applications, also food packaging. And if we one step further would be to do some deacetylation of the chitin to produce some chitosan, and also we could compare this chitosan to the conventional one. Another thing would be to make only partial deproteinization of the chitin, and then we could first reduce the energy used to purify the fibers, and also or maybe observe some synergies. So I would like to thank you for your attention and everyone who participated in this project from Aalto University and the LGBTQ, and also the two companies that gave us the samples from the fly, S-fly, and from the mealworm, die farm. Thank you.
Yeah, thank you very much, Eva, for the very nice talk about the insects and chitin. I do have, or there are a few questions in Slido. I will do it first come, first serve. So actually, the first question that was posted was, how did you solubilize the chitin to perform the NMR analysis? Or was it solid state? Is it soluble?
Yeah,
it's not soluble.
It was solid state. Yeah.
Okay, so it's solid state NMR. Okay, now I'm a bit, because of time. Okay, I will start from the top. I'm sorry. So at which temperature did you perform your hot and cold press?
So the hot press was at 90 degrees, and cold press, it was room temperature.
Mm-hmm. Then there was another question, I think you mentioned, but maybe it was not. So why did the purified material contain chitin and cellulose in 50-50 ratio?
Yeah, so this sample was obtained from a farm, the worm farm here, and it was actually part of it was the skin of the mealworm that they removed when they grow, and it was mixed with the feed, so the food that they grow on, the substrate, it's also their food, and it's mixed together. So, and it's a cellulose-based substrate, and we took the waste as such. We didn't separate the cellulose from the chitin-based products, and we purified everything together and then use it, as such. So that's why we have a lot of cellulose.
Okay, it's the food actually that makes the cellulose. Good.
Yeah.
Then the other question is, have you done warm chitin film with the hot press process?
So we haven't done it because we've seen that the cold press gave higher properties. So we only did the cold press for the worm.
Mm-hmm. Okay. Then there is another one. So it's about the industrial feasibility. Do you see industrial feasibility for insect culture with the purpose of material extraction compared to that of crustaceans? So can it be industrially upscaled or used? Is it better actually than shrimp?
Yeah, so I think it can be done industrially because they are actually now doing the insect farming. So if we just take the products that they are not using, and this skin from the mealworm, for example, you cannot extract, it's not worth to extract the protein because it's really low amount of protein in that. And then I think it could be an opportunity to extract the chitin from it. because they are not doing anything from it. So if we can take it and extract the chitin and then make some materials with it, then I think it's promising.
Okay. And related to that, by the same person asking a question before, which insect would you pick for that purpose? Considering the properties of films and the availability of the biomass.
Yeah, so now the company that are growing, they only use two kind of insects, and that's the mealworm and the black soldier fly. So the two that I used, and I don't know exactly why these two are the most used, but they are the one that are at industrial scale now.
Okay. Yeah, thanks a lot, Eva. I would suggest to move on to the next speaker. Thank you very much for your talk. And the next talk will be given